Hello all. So in this lecture, we'll see how to find minimal set of functional dependencies and also how to find keys of a relationship. So this is the outline of this lecture. We'll first see what is this minimal set of functional dependencies. Then we'll see an algorithm to find minimal cover or minimal set of functional dependencies. We'll see some examples and also we'll see an example to find key of a relation. So minimal set of functional dependencies. In the previous lecture, we have applied inference rules, expand a set of F of functional dependencies to arrive or to find F closure. So we applied inference rules on F and we derived F closure. So now we will think in the opposite direction to see if we could shrink or reduce the set F to its minimal form. So F closure is the maximum set of functional dependencies. If we could reduce it to a simpler form so that the minimal set is still equivalent to the original set F. So if we could reduce that F closure to a minimal form, which is equivalent to the original F, then it will be much more useful to use. Because when we perform design by synthesis method, the first step in design by synthesis is actually to find the minimal set of functional dependencies or minimal cover. That's why we learned this thing. The minimal set of functional dependencies, it can be defined informally like this. Minimal set of functional dependencies or minimal cover of a set of functional dependency E is a set of functional dependency F. So minimal cover is also a set F that satisfies the property that every dependency in E is in the closure F plus of F. So if you have a set E and if you want to find the minimal cover, then it will be another set F, and if we take F closure, all the dependencies in E will be there in F closure. Then we can say it is minimal. And also F must not have any redundancies in it. There should not be any redundant function dependency in the set. And dependencies in F should be in standard form or canonical form. So what do you mean with the standard form or canonical form? So if the right hand side attribute contains only a single attribute, then it is known as standard form or canonical form. For example, SSN to name. RHS is the name is the RHS. So name is a single attribute. So if you have only a single attribute in RHS side, then it is known as standard form. So minimal cover, it should satisfy this condition. Then it should have no redundant functional dependency in it. Also, the dependencies in F should be in standard form. We will see how to find these things later. Before going into this minimal cover, we should learn what you mean by this extraneous attribute, extraneous or irrelevant attributes. So this is the definition for an extraneous attribute. An attribute in a functional dependency is considered an extraneous attribute if we can remove it without changing the closure of the set of functional dependencies. Then that attribute is known as extraneous attribute or irrelevant attributes. So if you take some relations and if you take the functional dependencies, some attributes may be irrelevant for that functional dependency or it may be considered as extraneous. So such kind of attributes should be removed from those functional dependencies. So given F, the set of functional dependencies F, and a functional dependency x to a in F, then attribute y is extraneous in X if y is a proper subset of X. So y is a subset of X, it is extraneous. So X contains y. And F logically implies this. That is, if we remove, let me take out this pointer. So if we remove this attribute x to a from F and we add, this is union operation, we are adding a new functional dependency. And that functional dependency is got by removing y from x. And we have this functional dependency x minus y to a. Then we are adding this functional dependency to the original F. So we have removed this x to a and we are adding a new functional dependency by removing this y attribute. Then y attribute is known as extraneous attribute. So we will see this example, a simple example. We have a relation ABC and we have a functional dependency AB to C and A to C. Then if we take the closure of F we will get ABC, AB to C and A to C. There is no other functional dependency which can be derived from these functional dependencies. Here B is extraneous because A to C means here we have a functional dependency A to C. So A to C means A alone can determine C. So so here is this functional dependency AB to C is there, but there is another functional dependency A to C. Here C C is alone determined alone by A. So here B is actually extraneous attribute. So we can remove this B attribute and we will get A to C. So the functional dependency can be simplified to F equal to A to C. So in this manner we can minimize that. So because B is extraneous in this set of functional dependencies, this is the thing we have done here. We are removing that AB to C functional dependency and we are removing the B from it. AB minus B will be A to C. Here it will be C. A to C will be there. So we can remove that extraneous attribute. We will see another example how to find this extraneous attribute. Then you will understand how to get this extraneous attribute. So how to find extraneous attribute? So we have two types of extraneous attributes. One type of extraneous attributes occur in the LHS of functional dependency, left hand side of functional dependency, and another type of extraneous attributes can occur in the RHS, right hand side of functional dependency. In the case of minimal cover, we need to consider only the left-hand side extraneous attributes. But I'll be going through both the cases because for some competitive exams or gate exams, these type of questions will be asked to find the extraneous attributes and remove these extraneous attributes from functional dependencies. So we'll see the first case. So in case 1, LHS extraneous attributes, we have functional dependency alpha to beta where alpha and beta are set of one or more attributes. So here alpha might be a single attribute or maybe a set of attributes, and beta might be also a single attribute or it may be a multiple attribute. Then case 1, left hand side of functional dependency, if we need to find whether an attribute is extraneous or not. So we have to check whether an attribute A in alpha is extraneous or not. For this, what you have to do is, in step 1, what you have to do is, we have to remove that attribute and find the attribute closure. So we have to remove A from alpha and we have to find the closure of that using the functional dependencies of F. Then in step 2, if alpha minus A, the hook closure, contains all the attributes beta, then A is extraneous. So this is simple. How to find this extraneous attributes? You have to remove that attribute from the alpha or from the X part and you have to find the closure. You know how to find the closure. You have seen the algorithm to find the closure. And if you get the closure and if beta is present in that closure, then A is an extraneous attribute. We will see with an example. So this is important. So if you have a set F with P to Q and PQ to R, we have to find whether Q is an extraneous attribute in PQ to R. We have to find whether Q is extraneous in this functional dependency PQ to R. So for that, step 1, what we have to do, we have to find alpha minus A plus. So here alpha is PQ and A is Q. So we have to remove alpha is PQ and we have to do this. PQ minus Q closure, that is P closure. We have to find P closure based on this functional dependency. We have already seen the algorithm to find P closure. What we have to do, we have to take each functional dependency. For finding P closure, we have to take each functional dependency. First functional dependency is P to Q. So we have to add both P and Q to that functional dependency. P is a subset of P closure. So P is added. and RHS Q is also added. So we get PQ in that set. Then take the next functional dependency. We find that PQ to R. PQ is a subset of X closure, that is P closure, PQ. So R is also added. So the P closure will be set PQR. Now in second step, what you have to do? We have to check whether alpha minus A closure, that is P closure, contains all the attributes of beta. So here beta is R. So beta is R. R is present in P closure. So PQ minus P contains R. Hence Q is an extraneous attribute. So we can simply remove that attribute from the functional dependency and we will get PQ, P2Q and P2R. Instead of PQ to R, it will be P2R. So this way you can remove extraneous attribute. Then in the second case, we have to remove extraneous attribute from RHS, right hand side. So this is not important in the case of minimal cover. This is for if you want to answer some questions, you need this kind of information. This is not available in your Navodaya text. You have to refer some other text for this. So if we have a functional dependency alpha to beta, assume that alpha and beta are set of one or more attributes. In case 2, we have to remove RHS. We have to find if we have to check whether an attribute A in beta and the RHS side is extraneous or R not. So for that, what you have to do is we have to find alpha closure using the dependencies in F dash. It is not, we are not using F here, we are finding F dash. So here F dash will be like this. So F dash will be, we have to remove that alpha to beta functional dependency from F and we have to add another functional dependency, this alpha to beta minus A. That is from the right hand side, we are removing that A attribute from beta and we are adding that functional dependency to this F and this will be our new F dash and we have to find alpha closure in this F dash, not on F. So we have to find alpha closure on this F dash. And if alpha closure contains A, then A is extraneous. So we'll see an example, then you will understand what is this. So we have a set F with P to QR and Q to R. We have to find whether R is extraneous in P to QR. So R is extraneous in this right hand side. So we have to find alpha plus using this is the first step using F dash to this. So we'll say find F dash first. So F dash will be P to QR and Q to R. This is F minus P to QR. So we have to remove P to QR from this F. That's what we are doing this and we are performing a union operation with this P to QR minus R. We are removing that R from the right hand side. So we will get the whole functional dependency F as Q to R union P to Q and F dash will be like this. So we are simply removing this R from this. So the functional dependency will be P to Q and Q to R. This is step 1. Then in step 1 we have to find the alpha closure. So here alpha is P. Now we have to find P closure based on this F dash. So P closure will be, we have to take each functional dependency. We will take P to Q first, then P and Q will be added. Then we will take the second functional dependency Q to R. Then R also will be added. So closure of P will be PQR. Now in second step, what you have to do, if alpha plus contains A. So here A is R and alpha plus contains R. So A is extraneous. So in this case, P plus contains R. So R is extraneous to PQ2. So it is irrelevant. We can remove that. And the functional dependency will become P to Q and Q to R. So in this way, you can remove extraneous attributes from functional dependencies from left hand side and RHS. But in the case of cover, we have to deal only with the left hand side extraneous attributes. So we will see what you mean. What are the conditions for a minimal set of functional dependencies? So there are mainly 3 conditions for minimal set of functional dependencies. So first condition, every dependency in F as a single attribute for its right hand side. So every functional dependency should be in the canonical or standard form. That is, in the RHS part, there should be only a single attribute. So if there is a functional dependency x to ABC, we have to convert it into x to A, x to B, x to C. So we have already seen Armstrong's rule for that. So every dependency in F should have only a single attribute, should have only a single attribute for RHS. That is the first condition. Second condition, we cannot replace any dependency x to a in F with a dependency y to a, where y is a proper subset of x and still have a set of functional dependency that is equivalent to F. That is, there should not be any extraneous attribute in the left hand side of the functional dependency. That is the second condition. There should not be any extraneous attribute in the LHS of the functional dependencies. Third condition, we cannot remove any functional dependency from F and still have a set of functional dependency that is equivalent to F. Here we are taking if there are any redundant functional dependency in the whole set. So if there are any redundant functional dependency, we should remove such redundant functional dependencies. So these are the three conditions. In the first condition, we have to make it into a canonical or standard form. That is, R should contain only a single attribute. In the second case, we have to check for extraneous attribute in the LHS, left hand side of the functional dependency. And in the third condition, we have to check whether there are any functional dependency which are redundant. So we have an algorithm to find the minimal cover or minimal set of functional dependency. We call it as minimal cover algorithm. Here we give the input is a set of functional dependencies E. So what we do is we are assigning that set of functional dependencies to F. Then first condition, what we have to do, we have to replace each functional dependency x to a1, a2, etc. Like this, if there are functional dependencies like x to abc, we have to replace with x to a, x to b, x to c, so like this. So that is the first condition for minimal cover. So first cover, all should be in the canonical or standard form. So we have to make it into canonical or standard form. That is the first step. And in the second step, we have to remove extraneous attributes for each function. So we have to take each functional dependency x to a. We have to check attributes b in x. So if x is a set of attributes, we have to take each attribute in x and we have to remove that functional dependency like this. We have to remove b from x part and we have to add a new functional dependency into the original set, and we have to check whether f is equivalent to the original functional dependency. We will see how to find that. So in this, by doing this third step, we can remove all those extraneous attributes. Then in the third step, we have to remove functional dependency from F. We will try to remove each functional dependency from F and we will try to find whether it is equivalent to the original F. That is easy to find. We have to take the closure of F and we can see whether they are both are equal. So this is a minimal cover. So in the first step, you have to make it into canonical form. In the second step, you are removing extraneous attributes in the LHS. And in the third step, you have to remove redundant functional dependency. We will see with an example, then you will understand how it is to be done. So example 1, we will see two examples. First example, this is the first example. We have a set D to A, D to A, AB to D. So first step is to make it into canonical form. So canonical form means in the right hand side there should be only a single attribute. So if you check the functional dependency, we have only a single attribute here. We have only a single attribute in the RHS. Here also we have only a single attribute in the RHS. So all the three functional dependencies are in canonical form or in standard form. So we need not do anything. Step 1. Step 2. So we have to check for extraneous attribute in LHS. So here we have only single attribute. Here also we have only single attribute in LHS, but we have AB to D. So we have to check whether A is an extraneous attribute or B is an extraneous attribute in this. So we will check for AB to D. So we have to remove A. So how to check extraneous attribute? We have to remove A. So and we have to find D closure. using this functional dependency. So B closure will be A, then D will be added. So B closure will be, you know the algorithm for this, we have already seen this. So B closure will be BAD, and B closure contains D part, or this part is there. So A is extraneous. So we can remove A from A, B to D. So the functional dependency will become like this: B to A, D to A, and B to A. We can remove A from this because it is an extraneous attribute. Then in step 3, so now all the functional dependency have a single attribute in LHS. So we have no other extraneous attributes in LHS. Now we will check for redundant functional dependency. So in this example, if you see, there is a functional dependency B to D and D to A. So this implies B to A according to transitivity rule. So actually this functional dependency is redundant. So we can remove B to A because B to A can be derived from D to A and B to D. So we can remove this. So the final set will be D to A and B to D, and this will be the minimal cover. So in this way, first we have to check for canonical form, then we have to remove extraneous attribute, then we have to remove redundant functional dependency. We'll see another example. So this is another example. Here we G equal to A to B, C, D, E, and C, D to E. Now in step 1, we have to make it to canonical form. So we have to make it A to B, A to C, A to D, A to E, and C, D to E. Now in the second step, what we have to do, we have to find extraneous attribute in LHS. So here only one functional dependency is there where we have more than one attribute in LHS. So we have to check whether C is extraneous or D is extraneous in this functional dependency. For checking C in this CD to E, what we have to do, we have to remove C from this and we have to take D closure. So if we take D closure using the set of functional dependency, we will get only D. Only D will be added because there is no functional dependency with D in the LHS. So D closure will be D and E is not there in this set. So C is not an extraneous attribute. Now check for D, whether D is an extraneous attribute. We remove D from this. So and we will find C closure, and C closure will be set C. So C is also not an extraneous attribute. So all these functional dependencies should be there. And CD to E, in CD to E, C and D are not extraneous attributes. So CD to E should be there. In step 3, so C and C are not redundant attributes. And in step 3, we have to check whether there are any redundant functional dependency. So if we check for that, we can see that A to C and A to D, there are two functional dependencies, A to C and A to D, which can be written like this: A to CD. According to Armstrong's rules, A to CD will be written. So from A to CD and from the CD to E, we can imply this A to E. So A to E can be implied from A to CD and CD to E. So A to E is there. So this is a redundant functional dependency. So we can remove that A to E and the minimal cover will be A to B, A to C, A to D, and CD to E. So we can remove this A to E and we will get the minimal cover. So in this way we can find the minimal cover. So in order to find minimal cover, we have to make it into canonical form first. In the second step, we have to remove extraneous attribute from LHS. And in the third step, what we have to do, we have to remove any redundant functional dependency. So why do we study this minimal cover is that when we go for relational database design using synthesis, we will start with the set of functional dependency, and in the first step we have to find the minimal cover. Before going to normalization, we have to find this minimal cover, and this minimal cover will be the input to the algorithm. So minimal cover is an important thing when we do this synthesis, design by synthesis. But in your syllabus, it is not there. So this can also be written as F to A, B, B to C, D, A to B, C, D, and C, D to E. Then there is another simple algorithm to find key of a relation. How to find key of a particular table. So we have a relation R and a set of functional dependency F on the attributes of R. This is the input. So what we do is we set key. We set the key as R. All the attributes will be the key of that relation. That is the initial step. Then what we do is for each attribute A in K, we have to remove that. Compute K minus A closure. So from K, we have to remove any one of the attributes and we have to find the closure of K minus A closure with respect to F. If K minus A closure contains all the attributes in R, then K minus A, then set the key value to K minus A. Now the key will be the set of attributes with the removal of A. Then this algorithm will be repeated again and again. We have to remove one by one. We have to remove one attribute. Again, we have to check K minus A closure. And if all the attributes are there if K minus A closure contains all the attributes, then K minus A will be the key. Like that, we will go on removing. And finally, we may get with a key with 2 or 3 attributes. That combination will form the key. So in this way, you can find the key of a particular relation, but the order will depend on the order of removal of your attribute. So key will be varying for a particular person from person to person. It depends on the order by which you remove the attribute from this table. So this is the algorithm to find the key of a relation. So this is the thing we have seen. We have to see how to find the minimal cover. So that minimal cover is very important when you go for relation design by synthesis. So there are algorithms to find BCNF or to normalize into third normal form. In those algorithms, first step is to find the minimal cover of functional dependencies. After that, you have to perform that algorithm. So this is important topic. That's why. Thank you.